I hope the sound is working. This new mic headphone acts a little funny, but we will look at the phases finally in some systematic way. Remember, I mentioned the Rasmussen and Carpenter paper from 1982, which became, quite well cited because at that time it was the first one to really put together the phases of El Nino with many details, and then the 82-83 El Nino evolved differently than the composite they had made. Now we are back to doing composites. This is a paper, a review paper from I think one of the Nature franchises by Axel Timmerman and the gang. It looks again at so-called ENSO complexity, and it's showing the mean SST here with upwelling and cold SSTs in the east and warm SSTs on this side. It's showing over 29 degrees, and the color scale is not very dramatic, but you understand here. You see the pool of warm water with deep thermocline and the shallowing thermocline to the east. Typically, you look at averages over 2 south, 2 north, or 5 south, 5 north, or something, depending on what you are trying to argue. Here we are looking at the Nino 3 SSTA in degrees centigrade, going from minus 2.5 to 2.5, and the 20-degree isotherm depth anomalies going from minus 25 meters to plus 25 meters. You clearly see a very high correlation between them. There are lead lag relations based on the phases of El Nino and La Nina, and we'll see a bit more of that. But essentially, Bjerknes feedback requires that the thermocline movement affect the SSTs through mixed layer processes. There are many details. For example, strongest upwelling season is when the trade winds are strong, divergence at the surface, near surface is strong, thermocline is trying to get shallow, but you may have strong turbulent kinetic energy from the wind, so the mixed layer is trying to get deeper, so you are entraining cold water into the surface and making the SSTs the coldest. So you have to understand the balance that weak winds may reduce upwelling like in March, April, May. Thermocline may relax, but SST will be warmer, mixed layer may be shallower, and so on. So this stratification, entrainment, divergence, all these are interesting processes that determine totally how the SST and thermocline interactions work. Here we are looking at the evolution of the El Nino. So you have the onset phase here. Let's say we have some stochastic forcing. They're showing it like a twin cyclone as we saw in the Western Pacific oscillator, but we have the discharge phase already well in place here, April of year 0. This is not true as we saw for all El Niños. Strong El Niños tend to look like this, early onset, etc. So there is stochastic forcing of the westerly wind events, and downwelling Kelvin waves are involved. And you have the growth phase where now you begin to already see the recharge phase setting in, because you have exhausted the warm waters and beginning to create colder pool of anomaly on the other side. And this is by August of year 0. So this year we are in June of 2026. This is beginning to look somewhat like this, with cooler temperature anomalies on this side, warm anomalies well in place in the eastern Pacific, and the surface manifestation for an early onset is clear by August of year 0. So the nonlinear Bjerknes feedbacks kick in, which means the thermocline interactions with the mixed layer and the SST are very strong, and the surface interactions in terms of pressure anomaly, pressure gradient anomaly, and the wind response are very strong. So the whole process, the El Nino 3 is beginning to grow, and you can see here that the thermocline and the SST anomalies are close to zero in the beginning of the year, and the thermocline gets shallower, and with this range of the thermocline anomaly shown in the blue shades, and red is the Nino 3, and you can see it begins to get warm September, October. By December, January, February, it's beginning to wind down and the decay happens. So this is year +1, which is what we are going to get into here. So mature El Nino phase, December of year 0 is where you typically see the peak, and slowly it moves into January, February, and begins to decay. So you can see that the recharge phase. So if you plot the front between the warm fresh pool and the cold saline pool, then it would be going in this direction, but before December itself it will be going back, because the recharge phase and the subsurface processes are already happening. If you go forward to April of year 1, so year 1 now will be 2027, you can see that the SST anomaly at the surface is beginning to disintegrate. There are some details. Sun is to the south in December, January, February, so everything will be shifted south, as we'll see in the next podcast. And the cold anomalies are beginning to kick in, so trade winds are strengthening, and now you are setting off upwelling Kelvin wave with the easterly wind events, and cold tongue is beginning to emerge by the summer of year 1. It's a transition from El Nino to La Nina. So the La Nina typically tends to be fully manifest and in its mature phase by December of year 1. So you will have again Bjerknes feedback in the opposite direction. So you have cold SST anomalies, high pressure, low pressure, pressure gradient, stronger wind, stronger upwelling, and stronger thermocline mixed layer interactions and colder SST, so more cold water upwelling to the surface. Does this always happen like this? Not necessarily, but you can see that the standard deviation of Nino 3 going from about 0.8 to 1.2 or so, and then dropping off. This is the Nino 3 SSTA itself. This is the standard deviation. These are the growth rates of ENSO, so it's degrees centigrade per year. So you are getting stronger warming, and then before you reach the peak, the warming rates are declining, but SST reaches its peak, and then you begin to cool, and the cooling rate accelerates by here, for example, and then you begin to slow down the cooling rate as well. But the La Nina may revive and go for another year, but seasonal cycles will happen. So La Nina and El Nino peak in December, January, February. Upwelling is maximum in June, July, August. March, April, May is when spring warming happens, flattening of SST gradient happens. All those things happen, so the anomalous processes and the seasonal cycle work together. Okay. So this paper also presents the same the recharge-discharge figure we looked at before from Billy Kessler, looking at Nino 3 SSTA, La Nina on this side, El Nino on this side, and the 20-degree depth anomaly in meters, and it's showing again the charging phase. So La Nina is here in a fully recharged positive thermocline anomalies and cold SST anomalies in the Nino 3 region. El Nino events are on this side, positive SST anomalies and negative, typically negative depth, the thermocline depth anomalies if you have discharged and approaching the mature phase. But obviously during the nonlinear growth, you are still in the positive thermocline depth anomaly. So right now we are going into the discharge phase. Already it's on, but thermocline anomalies haven't started to become negative yet, and they will start in October, November of 2026, and they will get fully positive, it will come back here to the charge phase after the El Nino is done. So essentially you are looking here at some East Pacific El Ninos from 1991, the CP, so Central Pacific El Ninos and East Pacific El Ninos. So here you have 1972, 2015, 1982, 1997 on this side, and you have some Central Pacific El Ninos which are closer to the zero line here, obviously Nino 3 is going to be very small because the warming is more towards the dateline, and you have stochastic processes here, which is what I called weak El Niños before, but you can count CP El Niños into them. But this is just based on Nino 3. The impacts are more important. If a monsoon gets bigger drought during a CP ENSO, then we don't care whether you call it a weak El Nino or CP El Nino. We only care about what happens to the monsoon. So this is a schematic representation of ENSO temporal complexity. The paper basically talks about ENSO complexity. They make a similar complicated diagram for spatial complexity and talk about where the predictability comes from. If you are making ENSO predictions and we are saying ENSO is predictable up to 8 months, 9 months ahead, some people claim 2 years ahead and so on. Essentially, there is something in the system. Once it's on its way, it has a very systematic evolution, as we have said, and predictions are possible. And this year, obviously, it was predicted very early on in the year, just like 2023. But again, to remind ourselves, 2024 was predicted to be a La Nina and it didn't work out, and so on. Similar issues existed in 2012, 2014, and so on. So predictability is essentially where there is some memory in the system, like a Kelvin wave will, take some time to travel. There is ocean heat content. All these things have memory, and if the models can work on this memory, then you can have predictions. Predictability is basically the intrinsic theoretical quantity that says how predictable the event is, and models have to maximize observed predictability, but predictability itself is a model construct, so all kinds of complicated issues. Okay, so kernel density estimate of the joint probability distribution in orange shading of the linearly detrended Nino 3 SSTA and zonal mean 20 degree isotherm depth anomaly over 2 south 2 north 120 east to 80 west, so east to west, 2 south to north, for the period 1958 to 2016 from the merged data product. The gray circles indicate monthly values of the two time series. You can see the gray circles here in the thin line. They are smooth with a 3-month running mean filter to avoid a lot of variations. Dark and light blue triangles indicate December values of EP, so Eastern Pacific El Nino, and CP El Ninos respectively. Mixed events, so 1965, 91, and 2002. So the warming is not necessarily in the east or just around dateline. They are mixed. They are represented by combined dark and light blue triangles here, 91, 2002, somewhere in there, and so on. The years of the 5 largest El Nino events are indicated. White ellipse in the center corresponds to the progression of linear recharge oscillator, and arrows on the left and right indicate charging and discharging of subsurface warm water in the equatorial Pacific. So we said it's a recharge discharge oscillator, and then it has stochastic processes in them that we first called westerly wind events, and we called for multiplicative noise and so on. So that's what can explain the irregular periodicities, but it's phase locked to the annual cycle, and there are papers explaining why that phase locking happens and so on. Okay, so let's leave that there in terms of ENSO evolution. I don't know what happened there with the empty slide, but the figure is not appearing. Okay, so anyway, let's stop this and come back. I have to reopen the PowerPoint to avoid this issue. Okay, see you in the next podcast.